Hey, thank you for joining us at the Microsoft Research Summit 2021. I'm Yonatan Bisk from Carnegie Mellon University, and today I'm going to be talking about a new data set that we've just released as part of a NeurIPS challenge, WebQA, Multihop, and multimodal question answering. This is joint work with a number of collaborators around Microsoft Research, and the lead author on this is my student Yingshan Cheng, who I'll reference again later in the presentation. So what are we doing here, and what's sort of the point of this kind of data set and introducing a new challenge? So the idea here is that the way that we access the web when we're using it is that we'll type questions into these little boxes, and we assume that some magical engine is going to be able to find the answer, but that answer may not rely in text. It may rely in images or some other modality. So we're trying to take one step towards moving models towards the kinds of web experiences that humans have. So let me make that more concrete. I have a question like, are there picnic tables in Shenley Park? That's a local park here in Pittsburgh. So if I go to Bing and I search that, I'm going to get a couple of answers. So I might get this first one here saying that there's some sort of blanket and board in Pittsburgh is going to have some sort of a picnic maybe in Shenley Park. Doesn't answer my question. I might get this other thing about the Parks Department website, which is talking a little bit about some of the facilities, the fact that you can have picnics there, still not answering my question. So I've got these snippets which are semantically related, they're relevant, except that they're not actually what I'm looking for. And as a human, we sort of already would have guessed that. When I told you I was going to ask the question, are there picnic tables? You probably don't even look at these sets of search results. You don't even look at that main page of text because you know that there's this other tab that will just give you the answer immediately. So here we see it. The first thing is someone's picture of a picnic bench in Shenley Park. We also see some maybe picnic tables, which are not helpful. So it's not the case that every image is going to answer our question, but it is the case that some answers are just more readily accessible if we have access to a second modality, if we have access to, in this case, images. And so then what we want is that we eventually have some sort of a search engine. We have Bing or whatever it may be that basically takes in that question, aggregates the knowledge that's available to it across both of these modalities, and then produces a fluent answer. So yes, there are uncovered picnic benches in Shenley Park. Now, there may also be covered picnic benches, but we don't have evidence for that here. And so this is the kinds of reasoning that we would want it to have. It's sort of correct, it's multimodal, and it potentially uses multiple sources and cites them as part of that. Now, I also mentioned multi-hop in the title because there's also more complicated questions that we tend to see or that we might want to be able to ask a system. So for example, what type of currency was used during Cleopatra the Eighth's reign? It's a somewhat specific question. You can imagine these are the kinds of questions that children that are trying to cheat on their homework will tend to put into a search engine. And so what we need is we do get relevant information from Bing. So here we get something about Ptolemaic coinage, which is actually going to be the answer, but there's nothing here that specifies Cleopatra. We then get this other source that tells us about previous rulers and then a reference to this last queen, Cleopatra, and that she was during this age, that dynasty overlapped. And so what we need are both of those pieces of information to be aggregated so that we can actually produce an answer. In this case, just the simple phrase, Ptolemaic coinage. And so the idea here is that the kinds of things that you and I do when we walk up to a search engine are take a bunch of snippets, take a bunch of images, we have some preconceived notion of where the answer probably is going to be, and then some way that we might reconcile pieces of information in order to get the correct full answer. And we just want systems to be able to do that as well. Right now, the literature is largely split. So we have people that are focusing on these kinds of multi-hop questions in the text domain. We have people that are working on increasingly strong visual challenges, but we're not seeing something that's at that intersection that's doing the same thing that we're doing, aggregating across both. So what's the difference between questions that are being addressed to, for instance, images versus to text? Well, if we look at kind of a word cloud, this is from the data set that we've collected, you start to see things about libraries, artwork, churches, cathedrals, attractions. These are places, people, places, things, stuff that you see when you're out and about in the world. Very different from clinical psychology, natural history, these slightly more maybe academic topics that are sometimes present in the text corpora. And so again, in the same way that we know that if I'm looking to see if there's a picnic bench, an image is going to quickly answer the question, we want our systems to be able to do that, to be able to reason across both of these types of knowledge. So how do I know that, let's say, people are interested in these kinds of questions? Well, I know that they are because I ask these kinds of questions, I do this kind of reasoning, and everyone I've spoken to has fired off at least one query in the last week or month where they didn't think it was going to be that complicated, the system didn't answer it correctly, and they had to do a little bit of digging. The answers were there, but they had to find them for themselves. So we do know that people are asking these questions of web search, but they're not doing it at scale. So the correct answer in some sense to do people ask these questions of web search is no, because while they're there, they're very rare. We've all been trained out of it. We've all been trained that this question is probably a little bit too hard. And so I'm not gonna expect anything of it. And instead we put keywords in and then try to do multiple searches to aggregate the information. And the way that we know this, as I was saying, is this is rare, is that we actually went and looked at the Bing logs. So without going into too much more detail here, we know both from those logs that people are asking these questions, and we also know that it's pretty rare that they're actually either getting an answer or in general that they follow up with these kinds of things because they get sort of disheartened by the fact that there really just isn't the kind of response that they wanted when they thought it was probably something simple. So we have to address this problem. We can't just go and grab a bunch of logs and then answer those questions. We instead have to collect these questions artificially. We have to construct a scenario so that we can train systems so that in the future we don't have this problem. In the future we can deploy systems that are able to do this kind of complicated reasoning, this cross-modal reasoning, these kind of full sentence kinds of answers that you would want from an assistant. And that way, when people come to a search engine, they actually ask more of these things, and we get a nice sort of feedback loop because they're getting some of what they want, and so then they give us more data to increasingly sort of build robust systems. So how did we collect the data? So what we did was we had a bunch of users on Mechanical Turk, and this is for an image example here, that we showed them topically related images. So these may be based off of the same location or the same sort of type of structures, things like this. Annotators actually also proposed possible clusters that would be useful for us. And then we asked them, grab one or two of these images and ask a question that would sort of require information aggregation across them. So here you're seeing a simple interface. They choose 1, 2, 3, 4, 5, or 6. They write some sort of a question and they provide us an answer. Now we want to make sure that what they're providing us is correct. So we have a pretty rigorous validation process, which I'm not going to go into in too much detail here, but basically there's a sort of a correctness and an agreement aspect to it. So we have people go through and say like, are these images that are being used, are the facts that the person is relying on actually valid? Are these accurate? Are these, do they correctly merge to answer the question? And then we also run another validation where we have people, given the question and those same sources, produce their own answer. So we can see whether or not they're producing very similar sorts of answers so that we can get to a place where we have data that looks very much like what a human would want. So how much data are we talking about? So I'm going to break it up first by modality. So in terms of questions that rely on images, we're looking at an overall here just shy of around 20,000 examples. Same in the text. You see these are split up predominantly in train, and then we have a smaller dev and a larger test set. So overall, about 34,000 of these pairs for training. So that's the sources, the question, the answer, and then 5,000 for development and 7,500 or so for testing. The other thing is we want to make sure that there's no sort of obvious sort of artifacts in the data that people are going to be able to have their models pick up on. And so what we're doing here is in the same way that when you show up to a website, there's maybe the 2 facts that you need and 8 facts that are irrelevant. We also are going to parallel that with distractors in both modalities. So you have an image, the questions tend to be about 23 words on average, the answers maybe take about 21 words on average, and then you have 2 sources of additional text. So every image comes with captions and all text is a snippet. And so we're going to have sort of correct captions that are almost exactly the same length distributions as incorrect captions. Then similarly for the text side, we have this kind of thing with snippets being distractors that are sort of parallel in length. and you see the questions are similar in length between the two modalities. The answers are slightly different. So overall, we're not seeing anything where there's a clear giveaway that like, oh, there's a few more words here, it's probably the correct answer. That tends not to be the case, and so we don't have those kinds of spurious issues in the data. The other problem that we had to address in this work is how do you evaluate? So far we've just been saying like, okay, very intuitive paradigm. This is something that you and I do all the time. We're going to have our systems do something very similar. They're going to go through the facts. They're going to give us an answer, but that answer is natural language text. And if you have a system which is producing a full sentence, there's a whole different research agenda there on just how to do evaluation of NLG systems. So the way that we try to address this without sort of taking on that full challenge is breaking up the evaluation into two pieces. We have what is sort of a fluency score with a little bit of semantics mixed in. We're relying on BART's score for this. And then we have an accuracy, where we actually had annotators provide sort of what is the noun phrase, what is the key entity that answers this question, or maybe just the key property, so a color. And so we can check for those. We can also make sure that they're still producing fluent and coherent language. And then we can simply multiply those two scores together in order to give a sort of overall sense of how well a system is performing. So that's what the numbers are that you're about to see on the next slide. So we have how well can a model retrieve the right sources versus a human. Humans are much better at it. Um, how well can a system perform if it has predicted sources, and how well can a system or a human perform with sort of the ground truth sources. And the only thing I want to draw your attention to here very quickly is that while fluency really pretty impressive, accuracy really substantially different. And so there's definitely more that can be done in terms of language generation, make it sort of more natural sounding, but this is really the focus of this challenge. And that's also why you end up with this really big overall gap between humans and systems. So I wanted to kind of give you a few other little quick teasers before we close. So this gives you kind of a layout. There's an interactive version of this you can play around with of the types of questions that people are asking. But the important takeaway is that you have these kinds of questions broken up into a bunch of different semantic categories. Do the systems answer yes, no questions well? Can they choose between contrasting options well? Can they handle color questions, things like this? And you see that certain tasks are much harder than others. None of them are, in general, all that hard for humans. So in particular, I think this is not going to come as a surprise to anybody, but shape and number, can you reason about counts? Can you reason about inequalities? This is something that the systems that we currently have are just completely incapable of doing. They're looking to basically copy an answer from the text. They're not looking to reason, but you have to do a certain amount of reasoning if you're going to do multi-hop. You have to be able to aggregate information and knowledge and produce something new. The final column here, text-based, so these are the ones where we don't have sort of a clear maybe sort of finite set of answers. So yes and no being a finite set of just two. And so these are places where we're talking about sort of open domain entities, and we see that there's still a very substantial gap here. So in terms of knowing which entities in a snippet are related to the question, maybe the systems do an okay job, how those entities relate to each other, relate to properties of one another, still have quite a bit of ways to go. So where does that leave us? Well, it leaves us with a pretty long road ahead. So this is just one quick failure case that I thought was pretty funny. We have what is the sculpted bust at the Baroque Library, Prague, wearing on its head. And then we provide the image. So step one, figuring out that this is the bust that we're talking about. The systems are given access to some metadata that really shouldn't be a huge problem for them. It's something that even without metadata, humans don't really have a trouble figuring out if you have a contrasting set of things that are not busts. But what we see is that the model has said very fluently, the sculpted bust at the Baroque Library Prague is wearing a helmet on its head. And why helmet? Because that's a natural continuation. It's a totally fluent thing. The correct answer is obviously a flower wreath. So visual understanding, still going to take a while. Anyway, if you want to learn more about this, the paper can participate in the challenge. The website is here. There's a leaderboard for you to participate. And again, huge shout out to my student Yingshan Cheng, who's actually the lead on all of this collection. Thank you.